3 minutes ago, a signal that left a spacecraft 22 hours earlier finally landed on a radio dish in the Mojave Desert. Nobody in the room clapped. Nobody ran down a hallway shouting. But somewhere inside NASA's Deep Space Network, an engineer sat back in their chair and stared at a screen full of numbers that were not supposed to be possible. The spacecraft sending that signal is not new. It is not powerful. It is not even fully alive anymore. Not in the way it used to be. And yet right now, in the summer of 2026, it is doing something no machine built by human hands has ever done before. And it is forcing scientists to admit, quietly, carefully, in the language of peer review, that they got something fundamental wrong about the universe just outside our front door. This is the story of Voyager 1, and by the end of it, you are going to understand why the thing keeping engineers awake at night is not what this ancient spacecraft found. It is what it found, combined with the fact that it might only have a few years left to tell us anything else at all. Let's go back to where this actually starts, because most people only know the postcard version of this story. September 5th, 1977. A Titan Centaur rocket lifts off from Cape Canaveral, carrying a spacecraft built with less onboard computing power than the key fob that unlocks your car. The mission is not designed to be historic. It is designed to be efficient. Fly past Jupiter, fly past Saturn, take pictures, measure some particles, say goodbye. NASA budgeted for a 4 to 5 year mission. Somewhere in a filing cabinet in Pasadena, there was probably a memo about winding the whole thing down by 1981. Voyager 1 did not read that memo. It swept past Jupiter in 1979 and returned images so detailed that scientists discovered active volcanoes on the moon, Io, something nobody had predicted anywhere else in the solar system except Earth. Nobody on the mission team was expecting to rewrite a textbook that year. They were expecting some photographs and a graceful retirement a few years later. Instead, they got a moon spitting molten rock into space, and a spacecraft that clearly had no intention of stopping there. It swept past Saturn in 1980, used the planet's gravity like a slingshot, and kept going, and going, through the 1980s, through the 1990s, through the turn of the millennium, while the computer that was supposed to have died reciting its final readings kept quietly working, kept quietly listening, kept quietly sending its whisper of a signal back across a gap of empty space that grew wider every single day. By the time the 1990s were over, Voyager 1 had already become the most distant human-made object in existence, a title it has never once given up since. Then in 2012, 35 years after launch, Voyager 1 did something that took it out of the category of impressive old machine and into the category of the only one of its kind in existence. It crossed the heliopause. If that word means nothing to you, here's the picture. Our sun does not just throw light at us. It throws a constant outward stream of charged particles called the solar wind. And that wind inflates a kind of bubble around the entire solar system. A bubble that contains every planet, every moon, every asteroid, and every living thing we know of. The heliopause is the outer skin of that bubble, the place where the sun's wind finally runs out of push and the pressure of true interstellar space takes over. Cross that line, and you are no longer in the solar system. You are in the space between stars. In 2012, Voyager 1 crossed it. For the first time in the history of our species, a human-built object left the neighborhood of our own sun and entered interstellar space, and it kept transmitting on the way out. Think about the strangeness of that sentence for a second. We have had, for over a decade now, a working scientific instrument sitting in the actual gap between star systems. Not a telescope looking at it from a distance, not a computer model estimating what it might be like. An actual machine actually there, sending actual measurements home. And what it has been telling us since then is the reason we are having this conversation. For decades before Voyager 1 arrived, physicists built careful, rigorously tested models of what interstellar space should look like. Every one of those models described roughly the same thing: a calm, thin, mostly featureless plasma, drifting slowly, not doing much of anything, a kind of cosmic waiting room. Voyager 1 got there and found something closer to a storm. Starting in 2017, its plasma wave instrument began picking up a strange, narrow, persistent hum, a signal in the electromagnetic noise of interstellar space that, according to the models, should not exist in the form scientists were seeing. This wasn't a one-off blip that could be waved away as sensor noise. It has shown up again and again, year after year, across a stretch of interstellar space more than 900 million miles long. For comparison, the distance from Earth to the Sun is 93 million miles. This is a single continuous signal stretched across 10 times that distance. Recorded by one aging spacecraft with a plasma wave instrument older than most of the researchers now studying it. When the team analyzing this data published their findings in the journal Nature Astronomy, their language was unusually direct for a scientific paper. Interstellar space, they said, is not the smooth, quiet backdrop that decades of modeling had predicted. It has structure. It has turbulence at scales from a few meters all the way up to millions of miles. It behaves less like an empty hallway and more like an ocean, with currents and weather systems we never knew existed, because we had never had a single working sensor inside it to check. Sit with that number for a second, because it is easy to let it slide past you. 10 times the entire distance between our planet and the star that keeps us alive, and the signal never breaks, never fades into randomness, never resolves into something the old models can comfortably explain. It behaves less like background noise and more like weather with a pattern to it, structure sitting on top of structure, all the way down to scales you could measure with a tape measure and all the way up to scales you'd need a ruler, the length of a small planet's orbit to cover. That is the part that made the researchers uneasy, not that interstellar space had a signal in it, that the signal had a shape. Now here is where most videos about Voyager 1 stop, because this is already a strange enough story on its own. But it gets stranger and it gets more personal, because that turbulence out there does not stay out there. The same bubble that separates the solar system from that unpredictable outer environment is the same bubble shielding every living thing on this planet from the most energetic radiation the galaxy has to offer. The heliopause is not just a scientific curiosity marked on a diagram. It is a shield. And what Voyager 1 is telling us is that the environment pressing against the outside of that shield is more energetic, more variable, and more structurally complex than any model built from Earth ever accounted for. Nobody is claiming the sky is about to fall. But the honest answer from the people who study this is that we do not yet fully understand how a more turbulent, more dynamic interstellar environment interacts with the long-term stability of the very shield that makes life on Earth possible the way it currently is. And the fact that serious researchers now have to ask that question at all is itself new. Then there's the second discovery, the one that quietly rewrote a textbook assumption. For decades, the working theory was that the sun's magnetic field and the galaxy's magnetic field were two separate systems, cleanly divided at the heliopause boundary, like two rivers meeting the sea without ever really mixing. Voyager 1's data suggested something else entirely. At the boundary, the sun's magnetic field lines appear to be interacting with the galaxy's magnetic field lines through a process called magnetic reconnection, where field lines from different sources rearrange and exchange energy. In plain terms, our solar system is not magnetically sealed off from the rest of the galaxy, the way scientists assumed. It is linked to it. Energy is moving across that boundary in ways nobody predicted before an actual instrument sat there and measured it directly. Now, about that 3 minutes ago moment, because this spacecraft nearly did not make it to say any of this. In late 2023, Voyager 1 started transmitting nothing but garbled, unreadable static back to Earth. Not silence. Something almost worse than silence. A signal that was clearly alive, clearly trying to say something, but scrambled into nonsense that the most experienced engineers at the Jet Propulsion Laboratory could not decode. For nearly 5 months, the team worked the problem with no guarantee it was solvable at all. The cause turned out to be one single memory chip, a physical component the size of a fingernail that had degraded after 46 years of continuous exposure to cosmic radiation. That chip was corrupting the exact section of code responsible for packaging and transmitting scientific data. Here is what made fixing it almost unbearable. The spacecraft was roughly 15 billion miles away, a radio signal moving at the literal speed of light, the fastest anything can travel in this universe, took 22 hours just to reach it. Another 22 hours for any response to come back. Every single test, every single theory, every attempt at a fix required a minimum of 44 hours just to complete one round of communication. And every single command carried the real risk that one wrong instruction could end the mission permanently, with absolutely no way to send a repair crew. The team could not replace the chip, so instead, they relocated the corrupted code, breaking it into smaller sections, rewriting each piece to function correctly from a new location in the spacecraft's limited memory, and rebuilding the whole system to work together again. It was, in effect, remote brain surgery on a machine older than most of the people performing it, done across a communication gap of nearly 2 days per exchange. In 2024, it worked. Voyager 1 came back online, clean signal, full data, and immediately resumed sending back more of that same unexplained plasma turbulence from interstellar space, as if it had never even paused. Think about what that team actually lived through for those 5 months. Every morning, walking into a control room to look at a wall of numbers that should have meant something and instead meant nothing. Knowing the spacecraft was still alive, still burning through its last decades of power, but no longer able to tell anyone what it was seeing. There was no backup Voyager 1 sitting in a warehouse somewhere. There was no way to launch a replacement and catch up to 15 billion miles of head start. Whatever they figured out, they had to figure out with the one spacecraft they had, using nothing but patience, mathematics, and a communication line slower than anything most engineers will ever work with in their careers. That near-death experience is exactly why what's happening in 2026 matters so much. Voyager 1 runs on 3 radioisotope thermoelectric generators, essentially containers of decaying plutonium-238 that convert heat into electricity. At launch, they produced about 470 watts. Today, after nearly 49 years, they produce roughly 250 watts, and that number drops by about 4 watts every single year. Of the 10 scientific instruments Voyager 1 launched with, 7 have already been permanently switched off, one by one, in a carefully sequenced shutdown designed to squeeze the maximum possible science out of a shrinking power budget. Every instrument the team turns off is a set of questions that will never get answered, because there is no way to turn one back on once it goes dark. But here's the part that almost nobody outside the mission team is talking about right now. Engineers at JPL have been quietly testing something informally referred to inside the program as the Big Bang procedure, an experimental attempt to restructure how power flows through the spacecraft's aging systems in order to squeeze out a little more usable electricity from components running below their original efficiency. It is risky. There is no manual override 15 billion miles away, and no way to undo a mistake. So the team tested the concept first on Voyager 1's twin, Voyager 2, which has slightly more power margin and sits somewhat closer to Earth, making any failure less catastrophic. Those tests were run earlier this year. If they hold up, the same procedure could be attempted on Voyager 1 itself, with the earliest possible window opening this month. And if it works, there is a real chance that one of the recently shut down instruments, the one responsible for measuring low-energy charged particles, could be switched back on. Nobody at NASA is promising that, but nobody's ruling it out either, because with this particular spacecraft, betting against it has never once paid off. And then there's the date, already sitting on the calendar, locked in, completely independent of whether the power procedure works or not. On November 18th, 2026, at 16 minutes and 12 seconds past 2 in the morning Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth 1 light day. That means a radio signal moving at the fastest speed physically possible in this universe. I will take a full 24 hours just to reach it, and another full day for any reply to come home. Send a message on a Monday, and you will not know if it even arrived until Tuesday, and you will not hear back until Wednesday. No object built by human hands has ever been that far from home while still alive and still talking to us, and it will keep going. Every hour, it puts another roughly 38,000 miles between itself and Earth. The power keeps shrinking, the communication delay keeps growing, and sometime in the early 2030s, by every current projection, the last usable instrument will fall below the minimum power threshold it needs to function, and Voyager 1 will send its final readable signal home. But it will not stop moving. There is nothing out there to stop it. No friction, no atmosphere, no meaningful gravity to pull it off course. It will keep traveling in a straight line at roughly 38,000 miles an hour into darkness that has no end on any timescale a human being can meaningfully picture. And bolted to its frame, riding along for that entire silent journey, is the Voyager Golden Record, a gold-plated copper disc carrying greetings recorded in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter, and 90 minutes of music pulled from cultures across the whole of recorded history. It will still be traveling long after every city, every book, every name we've ever carved into stone has been erased by time. It will still be out there when the sun itself swells into a red giant and swallows the orbit the Earth currently sits in. It may be the single most durable object our species has ever created, and it is riding on a spacecraft that right now runs on less electricity than the light bulb inside your refrigerator. Whoever or whatever eventually encounters it, whether that is another civilization millions of years from now or something we don't currently have a word for, well, that record will tell them the same simple truth. A species existed here, curious enough to build a machine and send it past everything it had ever known, carrying nothing more dramatic than the sound of its own rain, its own oceans, and its own laughter. Here's the piece of this that scientists still cannot fully settle, and it's the actual open question sitting behind everything Voyager 1 has been quietly reporting since 2017. That persistent plasma emission, the strange hum stretching across 900 million miles of interstellar space, has 2 possible explanations, and researchers genuinely do not yet know which one is correct. One possibility is that it comes from ordinary thermally excited plasma oscillations, the natural vibration of charged particles bumping into their surroundings. That would be a real discovery, but one that fits comfortably inside existing physics. The other possibility is something called quasi-thermal noise, a different physical mechanism entirely, one that would require significant portions of our existing model of interstellar space to be rewritten. Telling these two apart requires either more data from Voyager 1, which produces less of it every single year as more instruments go dark, or an entirely new mission built specifically to study interstellar space directly. No such mission currently exists. No such mission is currently funded. If one were approved and launched today, it would not reach the heliopause for at least another 25 years. Which means that when Voyager 1 finally goes silent, whichever explanation is correct, the question stays open. The only real-time window our civilization has ever had into the space between stars closes, and it stays closed for a generation, maybe longer. It's worth pausing on why this particular question matters beyond pure curiosity. If it turns out to be ordinary thermal plasma oscillation, that's a tidy discovery, a new data point slotted neatly into physics we already trust. But if it turns out to be quasi-thermal noise, that points to a fundamentally different relationship between charged particles and the magnetic environment out there, one that would ripple back into how scientists model the density and behavior of the material pressing against our heliosphere from the outside, which in turn feeds directly into that earlier question about how stable our own cosmic shield really is over long timescales. In other words, this isn't an abstract argument between two categories of plasma physics happening in a room full of people arguing over a graph. It's a fork in the road for understanding the mechanics of the exact bubble that has allowed life on this planet to exist relatively undisturbed for billions of years. And right now, the only object capable of settling that argument is the one running out of power to keep asking the question. So here's what I want you to actually sit with. Right now, in 2026, the only living scientific instrument humanity has ever placed in interstellar space was built using technology older than the pocket calculator. It runs on less power than a kitchen appliance. It nearly died in 2023 and came back. It is about to cross a distance no human-made object has ever reached while still alive. And every single thing it has told us about the space beyond our sun's protection has turned out to be more turbulent, more connected, and more unpredictable than the smartest people on this planet had modeled it to be. We have built bigger machines since 1977. We have built more expensive ones, more powerful ones packed with technology the spacecraft's designers couldn't have imagined. None of them have told us what Voyager 1 has told us, because none of them have had the one thing this machine had: enough time and enough stubbornness to actually get there and keep talking on the way. There are questions about this universe that simply cannot be answered from a comfortable distance. Not from a telescope on a mountaintop, not from a satellite parked in Earth orbit, not from a lab full of the best supercomputers money can buy. Some answers only exist on the other side of a boundary that has to be physically crossed, and right now we have exactly one machine that has crossed it, and is still willing to talk to us about what it found. The signal is still coming. 22 hours late, carrying a report from a part of the universe no other instrument has ever touched, and once it stops, we don't get another one for a very long time. If this is the kind of story you want more of, hit subscribe, turn on notifications, and drop a comment telling me what part of this surprised you most, because Voyager 1 isn't done talking yet, and neither are we.